This next lesson is going to give us a big overview of quite a few of the different parts of rational functions. So this will actually serve to allow you to do 2 or 3 of the worksheets in the packet. So as we've already talked about, it's rational functions that we're dealing with, which kind of the definition is when you have 2 polynomials divided. So last chapter is all about polynomial functions. If we take 2 of those functions and put them in a fraction together, we get a rational function. Of course, the most basic is the one that we've talked about already, 1 over x, and that looks like this. You know, we've got a vertical asymptote, we've got a horizontal asymptote. Some more complex ones will make our graphs change a little bit because we are going to start having multiple vertical asymptotes. We will still most of the time just have one horizontal asymptote, but there could be more. But you start getting these more complicated graphs. And this, you know, if I gave you this, this isn't something you could graph just from a transformation. There's no shifting or you know, compressing or expanding here. So we need some different tools to graph these more complex rational functions. So we're going to look at just the major parts of the graph. Just like most other graphs, we've got end behavior. We need to know what's happening to the x as the x values approach very large numbers. So what that would be on our graph is this end behavior here. What's happening as my x values get bigger and bigger and bigger? So as my x values get closer and closer to infinity, what's going to happen to my graph? Is it gonna level out like this one's doing? Is it going to continue to go up to infinity? Is it going to go down to negative infinity?
Someone needs to hold their Ford vehicle that is parked in back by the egg shop.
So that's kind of what we're wondering. Okay, and also we need to know what's happening as we get towards very large negative numbers. Okay, what's this side of my graph going to do? We've got intercepts, same as other graphs. We need to know when it's crossing the x-axis as well as the y-axis. We have asymptotes, so values that the graph never touches. And there's 3 types of asymptotes. This lesson we're going to talk about the main 2, which are vertical and horizontal. So vertical asymptotes are the y values get very large as x approaches a value, okay, because a vertical asymptote, so if this is my asymptote, as x gets close to this, my y values are either going to follow it up or they can follow it down. So my y values are going to get very large positive or very large negative. Horizontal asymptotes, the y values are going to get closer and closer and closer to a certain number as x goes towards infinity. So if this is my horizontal asymptote, okay, maybe x is jumping around here, but then as x gets closer and closer and goes towards infinity, okay, it's going to get close to this horizontal asymptote. Okay, same thing this way. Maybe it's bouncing around, but then as it levels off, it's going to go this way. Something you should know about vertical asymptotes, you can't cross vertical asymptotes because those are the values where x does not exist. Okay, or those x values makes the function not exist. So you can never cross a vertical asymptote. Horizontal asymptotes, sometimes you'll end up bouncing up and down and cross them. So it's okay to cross your horizontal asymptotes. You cannot cross a vertical asymptote. The other part that's going to be on here are holes. These are problematic x values that were canceled from the top and bottom. So if my original function was x plus 5, x minus 2 over x minus 2. Okay, this is my original function. I can cancel this x minus 2 off, but I still couldn't actually put 2 into my function, because if I put 2 in, my original function doesn't have these things canceled out. So if I put 2 in, I'm going to be dividing by 0. So you have to remember that, and that's going to create a hole in your graph. So if I were to graph this, when I got to 2, okay, this graph is actually going to follow, because after I cross them off, I get just x plus 5. So I'd have just a linear function here. Okay, I'd have this function. But when I get to my value of 2, I should have an open circle at that value, because that value doesn't exist. So I put a 2 in, I'd be dividing by 0. Even though it's canceled out, okay, my original function did not have it canceled out, so you still have to respect the fact that a 2 made my original function undefined. So let's look at our first thing, end behavior. There's only 3 situations you're going to get into for end behavior. Okay, and they all depend on the leading coefficients and the first term of the numerator and the first term of the denominator. Okay, so our end behavior only depends on these, because end behavior is what's happening as x gets very large. Okay, so if x is very large, let's say 1,000,000, I'm going to put 1,000,000 in for all these x's. I'm going to have 1,000,000 to the 4th power. 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000. That's going to be such a huge number that this 1,000,000 to the 3rd power is going to be insignificant compared to the 1,000,000 to the 4th power. So when I get huge x values, these pretty much just get overshadowed by the size of my first term here. Same thing in the bottom. So I'm going to have 5 times 1,000,000 to the 4th over 2 times 1,000,000 to the 3rd. Okay, I'm just using 1,000,000 as my generic large number. But this 3rd, this 1,000,000 to the 3rd power, is going to be so much smaller than this 1,000,000 to the 4th. Okay, and you can think of it as 3 of my millions up here would cancel out and leave me with just 1,000,000. So I'd have a huge, huge number over 2, which is still going to be a huge, huge number. Now, if we think instead of 1,000,000 of infinity, okay, because these numbers are going to keep getting larger and larger, and this is going to approach infinity. Okay, and as we go towards negative infinity, well, then I'm going to have a very large negative, or a very large positive number here, because negative infinity to the 4th is going to become positive, over a small negative number. And as I go to the left, I'm going to be approaching negative infinity. So our end behavior here, so when your degree of your numerator is larger than the degree of the denominator, you're approaching infinity, either positive infinity or negative infinity. And which one it is really depends on which powers you have. Okay, so if I had 5x to the 6th and 2x to the 4th, well, now as I go to the right, I'm going to be approaching positive infinity. And as I go to the left, so as I put large negative numbers in, those negative numbers are going to both become positive here, so I'm going to be ending up with a large positive. So as I go left, I'm also going to be approaching positive infinity. Okay, but if the degree of the top is bigger than the bottom, you're approaching one of the infinities, either positive or negative, and you have to look at both directions to know which is which. If the degree of the numerator is smaller, we've kind of got the opposite situation. I'm going to have a very, very large number on the bottom here. Okay, and this top number is basically going to be nothing. Okay, it's going to be a very small number. So let's say we have 1 over a very large number. Okay, that's going to be a teeny tiny number. And the larger that this number gets, the smaller the number is we're going to have. And so it's going to be approaching 0. Okay, so this means our ends are both going to be approaching 0. As we go right, we're getting closer to 0. As we go left, we're getting closer to 0. Okay, so this is actually creating a horizontal asymptote at 0. If the degrees are the same, so here I've got to the 4th power to the 4th power. I'm going to have a large number times 5 over a large number times 2. Okay, because we can basically ignore these other numbers here. And these very large numbers are going to be the same large numbers, and they'll cancel, leaving me with just with the ratio of the leading coefficients. Okay, so when you have the same powers, as you go to the right, okay, your y values approach the ratio of your coefficients. So here I would be approaching 5/2. So I'm going to have a horizontal asymptote at 5/2. So I'll just take a quick second and show you the actual graphs of these, so you can see that it's actually doing this. Okay, so I've graphed some that meet all three criteria here. This red one is when we have the same power on the top and bottom. So my leading is 5x to the fourth, and on my bottom it's 2x to the fourth. So according to our rules, as we approach very large numbers, left or right, I should be getting closer and closer to a value of 5/2. Okay, so let me just put that line in here. Okay, so I should be getting closer and closer to this. Okay, so let's just scroll over here. Okay, you notice that actually on the left here, it's underneath my asymptote. It ended up crossing my horizontal asymptote here, but then it stays and gets closer and closer and closer. So that's an example of where you might cross your horizontal asymptote. And on the right side, I'm staying on the top of it and getting closer and closer and closer to it. If I could zoom in a little bit more here to give you guys more of an idea. Okay, there's 2.5. Okay, right there. You'll see as I move to the right, it's getting closer and closer and closer to that value. Okay, and it's actually never going to get there, but it's going to get closer and closer to it. If I go back to the left, oops. Okay, there it crosses it, and then it comes back and gets closer and closer and closer. So let's zoom back out here and look at the next example. In this one, I've got a power on the top that's bigger than the power on the bottom. Okay, and my power on top is even, power on the bottom is odd. So as I go to the right, I should be approaching positive infinity. And right now, I can't see that. But if I look up here, okay, here's the rest of my graph, and it is approaching positive infinity. Okay, and the left side should approach negative infinity, and it does that. Okay, it's just getting larger and larger negative numbers. So if I zoom out so you can kind of get the whole picture. Okay, here's way zoomed out, and my right side's going up to positive infinity, and my left side's going down to negative infinity. Let's look at the last example. So the last example is when we have a smaller power on top. So here, on top I have 5x to the third, and on bottom my leading term is 2x to the fourth. And my rules say we should approach 0. So if you notice, I'll zoom in here so we can get a good picture. Okay, as I go to the right, there's my graph. It's coming down and getting closer and closer and closer to 0. Okay, the farther over I go, the closer it gets to that 0. And as I go over here, okay, it's getting closer and closer to that 0 on the other side also. Okay, so that's just a couple quick graphs. And that covers end behavior. The next thing is how to find asymptotes. The vertical ones are where the bottom is 0. Okay, so the only thing you do to find your vertical asymptotes is set the denominator equal to 0. You solve those, and those will be your vertical asymptotes. Now, this first example, is actually one of the holes that I was talking about, because if I set x squared minus 1, okay, I can factor that into x plus 1 and x minus 1. So I've got x plus 1 on top, okay, and that'll cancel out here. So that means that I no longer have a vertical asymptote at -1. Okay, if you can see from my graph, there's no vertical asymptote here. But there is a hole on my graph right here. Okay, so I have to put that in my graph. There should be an open circle there so that you know that that value does not exist. So I've only got the one vertical asymptote here at, if I set this part equal to 0, I get x equals 1, and that's where my vertical asymptote is. And you can use all the same tools that we've used for finding zeros of functions. If it's quadratic, you can use quadratic formula. You can complete the square and set that equal to 0. You can factor. Factoring will come in quite often. Or you could go through the whole graphing procedure we had for the last test. Horizontal asymptotes we've already covered kind of by our end behavior rules. So, you know, if your degrees are the same on top and bottom, then you take the fraction formed by the leading coefficients, and that'll be your horizontal asymptote. If the degree on the top is smaller than the one on the bottom, then your x-axis is the horizontal asymptote. If the degree on top is larger than the one on the bottom, then you don't have a horizontal asymptote. Okay, and that's when it's approaching infinity and negative infinity. The other thing we need to know is how to find intercepts. And really, intercepts are when you have a y value of 0, okay, which you would do by plugging 0 in over here and solving. If you're doing that, you have to ask yourself, which part up here is really determining when this whole function equals 0? It's going to be the top, right? If the top is 0, then it doesn't matter what's on the bottom, you're going to have a 0. So you can ignore the bottom when you're finding intercepts and just set the top equal to 0 and solve it. So in this case, we could factor. I believe we can factor. Yep. So we can subtract 2 and subtract 1. And that means we would have zeros at 1/3 and 2. So those would be our zeros. They only come from the numerator. Okay, so the denominator determines our vertical asymptotes. The numerator determines our intercepts. And if we want a y-intercept, it's the same thing we do that we've always done to find a y-intercept. You just plug 0 in for x. So if I put 0 in here, this would go away, this would go away, this would go away, this would go away, and I get 2/9 as my y-intercept. So that'd be the point 0, 2/9. Okay, same thing here. You know, if I wanted to find my intercepts here, I could plug 0 in for x to get my y-intercept, so I'd get -75/9. And then, since this is a 4th power, I'd probably want to graph just the numerator and see where it crosses 0, and go through that whole process from last chapter to find all the zeros of this. But I could ignore the denominator, because that doesn't determine our intercepts. So that should be able to get you started on most of the first few worksheets. The next thing we'll cover in the next video will be slant asymptotes, which is the last type of asymptote. One of the worksheets in your packet is excluded values. Those are really the holes, so I'm just asking you to factor and cancel some things there and list which values were going to be excluded from your graph.